Hello everyone, welcome to this lecture video tutorial in Calculus 3. Enjoy learning. Hello everyone. In this lecture video, we will study a general procedure for deriving the power series for a function that has derivatives of all orders. That is, we will study Taylor and Maclaurin series. And as you have noticed in the previous lecture, which is lecture number 8, we derive power series for several functions using geometric series with term by term differentiations or integration. So without further delay, let's start our lesson. Okay, for our first definition, as you can see here, definition of the Taylor and power series. Okay, so you are given a function f of x which is of this form, which is a power series. Why is that? It is because in the previous discussion we know that a power series can be defined as a function whose domain is the interval of convergence. Okay, so this function now, which is in a power series form, the derivative exists at all orders at x is equal to a. Okay, then the Taylor series for f of x, this one at a, is given in this form. Okay, this is now the form. Let's have this color here. Okay, this is the form of the power series. What do you call this one? Can we make it bigger? Okay, this is the form of the Taylor series. Okay, this is the Taylor series of the function f of x at a. If our a is 0, okay, if our a is 0, as you can see here, this series is what we call the Maclaurin series. Okay, so if our a is 0, so let's have an explanation of this definition. Okay, let's try this black color. Discussion here, if f is a function defined by f of x, this one here, f of x, which is equal to this one, a sub n times x minus a to the n, where n starts from 0 to positive infinity. We will denote this function is here as a star. Okay, and if we expand this, we can write this one as a sub 0 x minus a to the 0. We know, let's move up, we know that in the previous discussion that this is 1 whenever a is x is equal to a also. Okay, although we have 0 raised to the power of 0 here, so we define this one as 1. Okay, if let's expand further, x minus a to the 1 plus a sub 2 x minus a to the 2 plus a sub 3, x minus a to the 3, and so on and so forth up to a sub n times x minus a to the power of n plus dot dot dot. Okay, so this is the expansion of this series. Okay, whose convergence, whose whose radius of convergence, radius of convergence is r, which is greater than 0. Okay, it follows from previous discussion. Okay, it follows from previous discussion that f has derivative of all orders on this interval, and I know that you are familiar with this interval. Our r is greater than 0. This is the interval of convergence. So we say that such a function is infinitely differentiable on negative r, this interval here. Okay, so meaning to say successive differentiation of the function in star gives this one here. Okay, let's try this color. So if we get the derivative f prime of x, derivative of this function here, this one, this function, this is 0. Okay, 0, this one is a1, 1 minus 1 is 0. Okay, so this is x minus a times the chain rule here. The derivative of x minus a is 1 minus 0. For the third term, this one a sub 2, we have 2a sub 2 x minus a to the power of 1 times the derivative of the x minus a is 1 minus 0. For the fourth term, we have a sub 3, no, not a sub 3, 3a sub 3, 3a sub 3 x minus a to the power of 2, okay, times the derivative of the x minus a is 1 minus 0, and so on and so forth. And the derivative of the n term is n, a sub n, x minus a to the power of n minus 1. Derivative of 1 x minus a is 1 minus 0 plus dot dot dot, and so on and so forth. Okay, so if we get the second derivative, so get the derivative of the first derivative. Okay, so we have here derivative of 0 is 0 plus derivative of this one here is 0 plus the derivative of the first term, second term, we have third term is 2a sub 2 x minus a to the power of 0. Derivative of this one is 1 minus 0. 1 minus 0 is 1. Okay, this will become 2 times, sorry, can we make it 3 times 2, and then a sub 3 x minus a to the power of 1. Derivative of x minus a is 1 minus 0 plus dot dot dot. Derivative of the n term is n times n minus 1 times a sub n x minus a to the power of n minus 2. This is 1 minus 0 plus dot dot dot. Okay, so continuing this process, let's try one more. Let's try to get the third derivative. Okay, so by getting the third derivative, we have to get the derivative of the second derivative. Okay, so derivative of the first term is 0 plus 0. This will become 0. And here we have 3 times 2. Let's say times 1 times a sub 3. We have x minus a to the power of 0. This is 1 minus 0 plus dot dot dot. This one becomes n times n minus 1 times n minus 2 times a sub n minus times x minus a raised to the power of n minus 3 times 1 minus 0, and so on and so forth. Okay, so continuing this process, and so on and so forth. Okay, etc. Okay, so if we letting x is equal to a in the power series, okay, in the power series of f and its derivatives, okay, we get, so this one here. So first let's try this one here. So if we substitute substitute here, let's try this color, f of 0. So what will happen is this will become 1. Okay, we define that 1 times 1, and this is 0 all throughout. Okay, okay, so this is this will become f of 0, which is equal to, and no, not 0, I think a, I'm sorry, this is a. So okay, this is a, I'm sorry, let's try to erase this one and replace by a, and this is f of a, which is equal to a sub 0. Okay, because a minus a is 0. Okay, 0 to the 1 is 0. So all throughout except the first term, we have, what remains is this form. So what will happen here is that a sub 0 is equal to f of a. Okay, f of a. Okay, and then for this one, if we replace x here by a, so what will happen, this will become f prime of a. What remains here is this one, a sub 1. Okay, a sub 1. Okay, and the rest, this one, the rest, this becomes 0 all throughout. This becomes 0. Okay, so a minus a is 0. 0 to the power of 0 is 1, as we define. Okay, so from here we have a1 is equal to f prime of a. Okay, and then and as you have noticed, this is over 1 factorial, and we can write this an over 0 factorial. We can see that later. Let's try getting the second derivative if we evaluate at x is equal to a. So if we evaluate this at x is equal to a, what will happen here is we have 2 here times 1 times a2. This will become 1. Okay, this become 1, but the rest is 0. Okay, 0 times that 1 is 0. So what will happen here, a sub 2 now will become f second derivative evaluated at a over 2 factorial. Okay, the 2 here, 2 times 1, this is 2 factorial. Okay, divide both sides by 2 times 1. Okay, so continuing this process, let's try the third derivative. We have here this one, this becomes 1, and the rest becomes 0. Okay, so this becomes 3 times 2 times, that's why I write this one here. We have a3. Okay, so a sub 3 here will become the third derivative of a over 3 factorial. And if you continue this process and so on and so forth, okay, if you continue this process, our an is equal to, there's a pattern, f of n, f to the n, this is the symbol of the derivative evaluated at a over n factorial. So meaning to say, if our n is 0, this is our function f of x. Okay, but if n is 1, that's the first derivative. If n is 2, that's the second derivative, and so on and so forth. Okay, so there's a problem here if we use the prime notation. If you evaluate the 10th derivative, then you cannot, of course, write 10 primes. Okay, so use this notation. Okay, this notation, the prime notation, is good only up to third derivative. But if you have if you evaluate the fourth derivative, the fifth derivative, and so on and so forth, then this will become ugly. Okay, so in general, this is the form of a sub n. Okay, so what will happen here, this one, thus our star here, thus star becomes, so we replace our an. So as you notice here, where is our star equation star? This is our equation star. Replace an here by the nth derivative evaluated at a over n factorial. Okay, so what will happen here, star becomes f of x. This is really a nice notation. The nth derivative evaluated at a over n factorial times x minus a to the power of n, where n starts from 0 to positive infinity. So this is now our what we call the Taylor series, and if our a is 0, then this is what we call the Maclaurin series. Okay, so let's have an example to illustrate this what they call this one, example, illustrate the definition. Let's have our example here. Let's say example number 1. Okay, find the Maclaurin series. Okay, Maclaurin series for e to the x. Okay, so this is our solution. Okay, so first we have to let f of x to be e to the x. Okay, then we have to get the derivative of all orders. Okay, so get the derivative. So what is our, let's wait for the program to respond. See here, then f of x, let's write the first definition, e to the x. Okay, then the derivative of, first derivative of e to the x is of course e to the x. The second derivative of e to the x is, you have to get the derivative of the first derivative, which is also e to the x, and so on and so forth. Okay, so as you notice, the derivatives are all the same. Okay, so and so on and so forth, and we know that the nth derivative, it has a pattern, but remember that this is not always the case. Okay, so why we write it this way? This is because we have to, what do you call this one? We have to evaluate our function, our derivative at x is at x is equal to a, which is 0. Why? Because we are going to find the Maclaurin series. Okay, so Maclaurin series says that our a is 0. So evaluate f of 0 is e to the 0, which is 1. F prime of 0, which is also e to the 0, which is 1. Second derivative, the same. Third derivative is also the same. Okay, sorry, up to the nth derivative, which is 1. So let's try to move upward. Thus the nth derivative is always equal to 1. Okay, for all n. Okay, so therefore the Maclaurin series, Maclaurin series for e to the x is given by this form. Okay, so substitute f of x. So this is the formula. So our formula is this one here. Sorry, we have 0 n factorial x minus 0 to the n. Okay, so substitute and then expand. So we expand this one, we have f of 0, which is our function, over 0 factorial times x to the 0. We have f first derivative over 1 factorial x to the 1. Okay, be patient, over 2 factorial x to the 2, and so on up to the nth derivative over n factorial x to the n plus dot dot dot. Okay, substitute. We have we have 1 here, 1, this is always equal to 1, 0 factorial, and this is 1, plus this is 1 over 1 factorial, x plus 1 over 2 factorial x squared, and so on and so forth, over 1 over n factorial x to the n plus that. Okay, so this is not always the case. There are times that you have to expand this form. This happens only because the expression of the a sub n is very easy, okay, which is always equal to 1. But this is not always the case. That's why I expand this form here. Okay, so anyway, let's go back to our notation, summation notation. This is x to the n over n factorial. N starts from 0 to positive infinity. And we know that this is a very familiar power series. We have an example, this one, in the this is an example in the previous discussion. I think lesson number 7 or number 8. Okay, so let's try another example using the example for the Taylor series. Okay, for our second example here, example number 2. Okay, find the Taylor series for cosine x at a, at x is equal to a. Okay, so solution. Again, we have to let our function to be, let f of x to be equal to cosine x. Okay, then get the derivative. So copy our function. Okay, first derivative of cosine is negative sign. Again, we will not use chain rule here because our x here, our u is x. Okay, the coefficient of x is 1, the exponent is 1. Okay, second derivative. So as you have noticed, there is no pattern, unlike the function in example number 1. Okay, let's see if we can have a pattern. The derivative of sine is positive cosine, so we have cosine x. Okay, the third derivative, okay, derivative of cosine is negative sign, so negative times negative, so we have positive, so this is positive sine x. Okay, so as you can see, let's try more, maybe up to 10th derivative. Again, our notation here, we will use f raised to the power close parenthesis of 4. Okay, we will use now the notation that we discussed earlier. The derivative of sine is positive cosine. Okay, so after the fourth, 1, 2, 3, 4, we go back to the original function. Okay, so let's try the fifth derivative. So again, this is negative sine x, which is the first derivative. Okay, we have the sixth derivative. We have negative cosine x. Okay, and then we have the seventh derivative. We have sine x. Okay, and so on and so forth. Okay, we have a dog there barking somewhere. Sorry for that. Okay, let's try to evaluate x is equal to a. Okay, So let's wait for the program to respond. This one. Of course, if our A is not let's say 0, or we have Maclaurin series, then I guess we can have a pattern here. Okay, so f of A, we have cosine A. F prime of A, which is negative sine A. Second derivative is negative cosine A. We have third derivative, we have sine A, and so on and so forth. Fourth, we have fifth, we have sixth, we have 7, we have cosine A, negative sine A, negative cosine A, and then we have sine A. Okay, so we cannot find a pattern, I guess, to write it in simple form. Thus the Taylor series for cosine x at x is equal to A is given by, we have that one. Let's try summation of what's the formula? This, I guess this is the formula, over n factorial. N starts from 0 to positive infinity. We have x minus A. Sorry, maybe I made a mistake. Not x is equal to A. At A, I guess. Maybe I was wrong. Let me check it first. I guess this is not A. I've checked it. I guess this is at A. Okay, this should be at A. Let's go back above here. At A. Okay. Maybe we have to wait again for the program to respond. So at A. So if we try to expand this, so the first term is we have 0. So this is cosine A. Okay? Cosine A over 0 factorial times x minus A to the power of 0. Okay, the first derivative here is let's see, negative sine A. So let's go back. Negative sine A over 1 factorial times x minus A to the power of 1. The third term is again negative. We have negative cosine A over 2 factorial times x minus A to the power of 2. So let's try to expand more. For first derivative, second derivative, this is the third derivative. third derivative is sine A over 3 factorial times x minus a to the power of 3. Let's try to add more up to 7. This is the third derivative. The fourth derivative is cosine A over 4 factorial. Let's move up. 4 factorial times x minus a to the power of 4. Plus for the fifth derivative is we have minus sine A over 5 factorial times x minus a to the power of 5. The sixth derivative is minus cosine A over 6 factorial times x minus a to the power of 6 plus, again we have positive, sine A over 7 factorial x minus, let's move up, a to the power of 7 plus dot dot dot. Okay, so this is your this is our Taylor series for cosine x at a. Okay, so meaning to say we cannot write the right hand side, this side here, into a simple form, meaning in summation notation, because we cannot find any pattern. But if ever that there is a pattern, we have to express it in summation form. Okay, so let's try maybe another example, or let's have a theorem first. Okay, a theorem first before another example, where we can have an example where we can express the right hand side into a simple form in a summation notation. Okay, so let's have a theorem first. Okay, further explanation of the Taylor series and some reminders. Okay, okay, I remember that I am going to give a theorem first before an example, but I changed my mind. First, before the theorem, I'm going to give a note first. Let's have a note here. Note that in the discussion above about the definition, we know that we have to get the first derivative of the function evaluated at a number a. First is I am going to give a note here. Notice that we can in the discussion we can deduce that a power series representation of a function is unique. Okay, why is that? It is because if two functions have the same function values. Okay, just imagine this in some interval. Okay, interval containing the number a, and if both functions have a power series representation. Okay, in x minus a, please analyze this note. Then, okay, what will happen? This series must be the same. Because the reason is because the coefficients in the series are obtained from the values of the functions and their derivatives at a number a. Okay, so please remember that if you are given two functions, okay, if you are given two functions and have the same function values, meaning to say if you evaluate the function uh, at that value in a given interval containing a, and if both functions have the same power series representation x minus a, then this series must be the same, because as we know in the discussion above, we evaluate the values of the functions and their derivatives at a number a. Okay, so please recall that. Okay, you example, if you have functions f of x which is equal to based on our example, we have cosine x, then we have to get the derivative, evaluate it at a, get the second derivative, get the third derivative, and so on and so forth. Okay, so what will happen here, therefore if a function has a power series representation in x minus a, this series must be its Taylor series at a number a. So what does this mean? So hence the Taylor series for a given function does not have to be obtained by using the formula, okay, mentioned above. Okay, so what does this mean? Meaning to say there are functions that have different in structure of the Taylor series, but they are the same power series. Okay, they are the same power series. So that's what we mean by this note. Okay, so meaning to say, uh, okay, meaning to say, uh, any method uh, that gives a power series in x minus a, representing the function will be the Taylor series of Taylor series of the function. Okay, at number a. Okay, so take for example, okay, take for example if you have this one, okay, the power series in the power series of e to the x, we know that in the discussion before, we can write the power series as e to the no, not the series, the function e to the x. We can write this as e to the a times e to the x minus a. Okay, we know that this is that they are equal. Okay, but then if you substitute, this is a constant, and we can use in the previous example, let me write it here. Recall that before, what happened, can we, okay, this one, let me put it here, somewhere here. Okay, this one, recall that e to the x is equal to the summation of x to the n over n factorial. N starts from 0 to positive infinity. Okay, so as you can see here, if we substitute, if we replace it here in this power series representation of e to the x, if we replace x by x minus a, then we have this one, okay, times summation of x minus a to the power of n over n factorial, where n starts from 0 to positive infinity. Okay, so if you try to expand this, you will have 1 plus x minus a over 1 factorial plus x minus a to the power of 2 over 2 factorial, and so on and so forth, until x minus a to the power of n over n factorial plus dot dot dot. Okay, so although they have different in form in this recall here, they are just the same if you evaluate it at a given number. Of course, if that number belongs to the what do you call this one, the interval of convergence of that power series. Okay, so we can deduce here that the power series representation of a function is unique. Okay, so one question here is if a function, okay, if a function has a Taylor series in x minus a, having radius of convergence r, which is a positive number. The question is, does this Taylor series represent the function for all values of x in the interval of convergence. Okay, in the interval of convergence, this one, a minus r, a plus r. Okay, so that's the question. So what are we going to do now is to answer that question. What happened? There's something wrong with the, okay, so I guess this one moves somewhere here. Sorry for that. Okay, so to answer this question, let's have an illustration. Okay, let's have an illustration. Okay, so illustration of this question here. Okay, so suppose that you are given a function, let f be the function defined by this form, e to the negative 1 over x squared if x is not equal to 0, and 0 if x is equal to 0. Okay, okay, so again we have to wait for the program to respond. So the question is, find the Maclaurin series for f, and show that it converges for all values of x, but it represents only, okay, f of x only when x is equal to 0. Okay, so this what we call this one, this illustration answers the question above. Okay, so let's try to solve this. Okay, so first, what shall we do? This is a Maclaurin series, or a is equal to 0. So of course f of 0 is 0, okay, because based on the definition, So now get the derivative, okay, evaluated at 0. So notice that this is a what we call this function. This is a piecewise function, okay. This is a piecewise function, so this is not normal, so therefore we have to get the derivative of this function using the definition, okay. So as you can see in your calculus 1, the formula is we have x minus the formula is f of x. I don't know if you recall the formula, okay. So anyway, just scan your notes, okay. So this is this one. I don't know if you recall, okay, as x approaches to 0, and this will become 1 over x over e to the 1 over x squared as x approaches to 0. So using L'Hopital's rule, so just use L'Hopital's rule, and the answer will be this one. This is limit of negative 1 over x squared, get the derivative. So use LHR, okay. So as x approaches to 0, this will become e to the 1 over x squared times, of course, derivative of 1 over x squared is negative 2 over x cubed, okay. After simplifying, you will get x over 2e to the 1 over x squared as x approaches to 0, okay. So this is this is I don't know if you remember this one. So this is 0, okay. So do the same for the second derivative, okay, by a similar method using the definition of derivative and the L'Hopital's rule, okay. So we get 0 for every derivative, okay. So anyway, just compute and see if you evaluate the function at x approaches to a, but in this case our a is 0 since we are going to find the Maclaurin series, okay. So what happened here is the nth derivative is always equal to 0 for all n. So the conclusion is therefore the Maclaurin series Maclaurin series for the given function is this one. Okay, 0 plus 0 plus 0 plus. Okay. However, this series uh, converges to 0 for all x, but if x is not equal to 0, then our f of x, which is equal to e to the negative negative 1 over x squared, is not equal to 0. Okay, so this is, of course, this is not equal to 0. Okay, for all x, of course, which is not equal to 0. Okay, here the limit, I know that you are very familiar with this one. Okay, this is 0. Just get the left hand and the right hand limit. Okay, so based on this example, okay, based on this example, let's go back to the question. Okay, so what happened? Let's go back to the question. It says here, if a function has a Taylor series in x minus a having radius of convergence r, which is greater than 0, does this Taylor series represent the function for all values of x in the interval? Okay, so as you can see in the example, in this illustration, it doesn't represent for all values of x. It only represents when x is equal to 0. Okay, so this is what do we mean by this question. So the question now is there a method, okay, or a theorem on how to determine whether the function represented by its Taylor series, okay, a test, okay, whether a function is represented by its Taylor series. So that's what we do in this sorry for that one. Let me silent it first. Okay, so the question is there a method or a theorem or a shortcut that will give us a way on how to determine whether a function is represented by its Taylor series? So that's the theorem that I am going to write after this discussion. Okay, so I guess I am going to write it here first, sorry, to write it first, and then I'm going to come back to discuss that theorem. Okay, this is the theorem that will determine whether a function is represented by its Taylor series. So let me put it here. This is the theorem that gives a test for determining whether a function is represented by its Taylor series. Okay, so all you have to do is to uh, get the remainder of the function, and then if that remainder approaches to 0 as n uh, no, if that remainder is the limit of that remainder is 0 as n approaches to infinity, then we can say that the series is represented by its Taylor series. So let's read here. Read the theorem. You're given a function f such that f in all its derivatives, we know this one already, this one here, in some interval, or r here is the radius of convergence. Then the function is represented by its Taylor series and this form for all x. Remember that this is for all x, where your x is in this interval of convergence. So what will you do? This is the necessary and the sufficient condition. All you have to do is to get the remainder, okay, r sub n, and this remainder is denoted as this one, the n plus 1 derivative of psi sub n over n plus 1 factorial, quantity of n plus 1 factorial times x minus a raised to the power of n plus 1, where your psi sub n is between x and a. Okay, so where did we get this formula for r sub n? I know that this is familiar. Look at the our discussion before when we estimate the value of a series. Okay, this is just the same method. Okay, so all you have to do is to expand this one up to n. Okay, expand this one up to n. For example, let me write it here. This is f this is your function evaluated at a over 0 factorial plus first derivative evaluated at a over 1 factorial. We know that this when you raise to the power of 0 is 1. Okay, so this is x minus a to the power of 1 plus the second derivative evaluated at a over 2 factorial times x minus a to the power of 2, and so on. Let's try to expand it here. This one here. Okay, up to the nth derivative evaluated at a over n factorial. Sorry. We have to wait for the program to respond. What happened? Oops. I think plus over n factorial x minus a to the n. Okay, and then this is your remainder r sub n of x. Okay, the remaining. Okay, so this is this one. Okay, wait, just wait. Maybe let's have an example somewhere here. let's have an example. But before that, let me give a note here. Let's try this color blue, maybe. Okay, we just have to wait. Color blue, we have to put a note here that other forms. Okay, number one, other forms of the remainder, r sub n of x. This is what the r sub n of x here is what we call the Lagrange form. Okay, this is what we call the Lagrange form. Okay, also holds. Okay, if you have other forms, second is it is often difficult to apply the theorem. Okay, the theorem in practice, because the values of psi sub n are arbitrary. Okay, arbitrary. This means that just look at the definition of the word arbitrary in the dictionary. Okay, so what we will do here, since it is difficult to apply the theorem, so what we do is to get the upper bound. Okay, however, sometimes an upper bound for r sub n of x can be found and we may be able to prove the limit of the upper bound is 0 as n approaches to positive infinity. And these are some formulas well known, or limit that are very useful in what they call this one, in choosing an upper bound. Okay, the following limit is helpful in some cases. Number one, you can use this well-known limit over n factorial as n approaches to positive infinity. This is 0 for all x. We know that in the topic about the rate of growth of convergence, I don't know what lesson, I forgot. This is familiar. Okay, n factorial grows faster than x to the n. Okay, the second is this one, the limit of x minus a to the n over n factorial as n approaches to positive infinity is equal to 0 for all x. Okay, so these are they have the same what you call this one, argument. Okay, in factorial is faster than x minus a raised to the power of n. Okay, so let's have an example. Okay, I'm going to write it here. Okay, let's have this example. Use the theorem above to show that the Maclaurin series for e to the x found in example number 1 in above represents the function for all values of x. So this is different from the conclusion when you say it is convergent for all x and it is convergent to that function for all x. Okay, that's a different story. Okay, so we know that the Maclaurin series for e to the x is this one, summation of x to the n over n factorial, and starts from 0 to positive infinity. Okay, thus, so what is the formula for our r sub n? Okay, thus our r sub n is equal to, based on the formula, this is f of n plus 1 of 0, since this is a Maclaurin series, over n plus 1 factorial times x minus 0 to the n plus 1. Okay, so what's the nth derivative here? Okay, so what's the nth derivative? We know that it is 1. Okay, it is 1, so we can substitute 1 here because the nth derivative of e to the x is e to the x evaluated at 0, which is 1. So this one in the numerator, this is positive 1. Okay, so it simplifies to okay, if we recall, maybe not this is not 0. I think this is psi sub n. Can we go back to the theorem? Okay, so maybe we have to wait for the program to respond. Let's go back to the theorem. This is okay, psi sub n. Okay, then x minus 0. Okay, so this must be, I'm sorry, this is can we go back? Okay, this is this one here. This is psi sub n. Okay, so we know that the n plus 1 derivative is equal to e to the x. Okay, so if we substitute psi sub n, okay, if we replace here, okay, replace psi sub n, so we have e to the psi sub n, so the numerator becomes e to the psi sub n, okay, over n plus 1 factorial times x to the n plus 1. Okay, so that's the formula for our remainder. Okay, so what are we going to show? To show here that the limit of r sub n of x as n approaches to positive infinity is equal to 0 based on the theorem. Okay, for all x. Okay, so we have to wait for the program to respond. So we have to consider three cases here, because it says here that we have for all x. So let's divide the problem into three cases. Okay, we have to consider three cases here. So the case where x is greater than 0, x is less than 0, and x is equal to 0. But this is not always the case. It depends upon the problem. Okay, so just analyze. So let's have case 1 here. Case 1 where x is greater than 0. Okay, so if x is greater than 0, then we know that our psi sub n is between this one. Okay, we pick our psi sub n to be between this one, 0 to x. Hence we know that e to the psi sub n is less than e to the x. This is obvious for the exponential function. So what will happen? We know that 0 is greater than e to the psi sub n over n plus 1 factorial times x to the n plus 1. Okay, since our x is greater than 0, as you can see here, so this is greater than 0. Okay, this is always positive, but we can bound, okay, from this inequality here. You can replace e to the psi sub n by e to the x. Okay, and then what remains here is that x to the n plus 1 over n plus 1 factorial. Okay, so why we did that? Because as you can see in the, if you remember in the discussion above, here we will use this what they call this one, this limit, well-known limit. Okay, so from 1 above, it follows that the limit of x to the n plus 1 over n plus 1 factorial as n approaches to positive infinity is 0. Okay, and so the limit of e to the x over n plus 1 factorial. What happened? Factorial as n approaches to positive infinity. Okay, this is a number. This is not related to this limit because our variable is n, and this is that is 0. Okay, this is a constant times 0, so we have this is 0. Okay, so this implies that the limit of r sub n of x as n approaches to positive infinity is 0, and by using the squeeze theorem. Okay, so recall this theorem in your calculus 1. Okay, so how about for the case number 2? Okay, case number 2. What happen if your x is less than 0? Okay, so if x is less than 0, then our psi sub n is between this one here, and so of course e to the psi sub n is less than 1. Okay, why is that? We have a negative 1 over, what do you call this one? We have a negative value here, so 1 over e to the psi sub n, where your psi sub n is between x and 0, then of course this is less than 1. Okay, this is very easy to understand. So therefore if x to the n plus 1 is greater than 0, then this one here, our inequality, remember, psi sub n plus 1 factorial times x to the n plus 1 is less than x to the n plus 1 over n plus 1 factorial. Okay, so this happens. So remember that this could be negative. It depends upon the value of n. Okay, if n is if n is even, we have even plus 1 is odd. Okay, so we have negative. If n is odd, we have odd plus 1 is even, so we have positive. So in this case, your n must be odd, so that n plus 1 is even. So negative raised to the even number is positive. So, and what will happen if x to the n plus 1 is less than 0? Okay, so meaning, what if it is negative? Then what will happen here is you have x to the n plus 1, so remember that this is negative, over n plus 1 factorial which is less than e to the psi sub n over n plus 1 factorial times x to the n plus 1, which is less than 0. Okay, why? Because this is negative, of course, and then what is the value of e to the psi sub n? This is positive, as you can see here. This is positive. Let's look at the inequality. Okay, so let's wait for the program. This is less than 1. Okay, so this is the here we have here less than 1. This is positive and this is negative, so therefore this is less than 0. Okay, so in either case, because the limit of x to the n plus 1 over n plus 1 factorial as n approaches to positive infinity is 0, it follows that the limit of r sub n as n approaches to positive infinity is 0. Okay, so for case 3, let's have case number 3. What if our x is 0? Okay, what if our x is 0? So let's move up. Okay, let's wait for the program to respond. So what happens here? Okay, so we have if x is equal to 0, so what will happen? Then the series has the sum of 1. Okay, which is e to the 0. Okay, so accordingly the series, this one, x to the n over n factorial, represents e to the x for all x. Okay, so that's how you are going to show if the series is represented by the given function for all x. Okay, for this topic, let's have a graphical interpretation of representation of functions by power series. So for illustration, okay, consider the power series. Okay, power series representation of e to the x. Okay, so which is this one, summation of x to the n over n factorial, where n starts from 0 to positive infinity. Okay, so if we let's say expand this one, this is when n is 0, so we have 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial x to the 4 over 4 factorial, and so on and so forth, up to x to the n over n factorial. Okay, so what we will do here is to graph the function. Okay, we are going to graph the function, and then let's estimate, okay, the function by its power series. Okay, so here let's have the Desmos calculator here. Okay, so this is the Desmos graphing calculator. So let's graph the function e to the x. So exp to the power of x. Okay, that one. Okay, the red one, this is our e to the x. Okay, the red one. So let's graph the when n is equal to 0. Let's say here when n is equal to 0, so we have 1. Okay, so when n is equal to 1, we have 1 plus x. When n is equal to 2, so we have 1 plus x plus 1 half x squared. So 2 factorial is 2. Let's add more, and cube into the n is equal to 3 is 1 plus x plus 1 half x squared plus 3 factorial is 3 times 2 times 1 is 1 over 6 x cubed. Okay, so let's try to graph this one. So when n is equal to 1, so we have y is equal to 1. Y is equal to 1. Am I right? This one here. So we have, okay, that one. Okay, y is equal to 1. So we have a line here. So it only captures 1 point of the exponential function. Okay, this point here. How about if we try to plot 1 plus x? Okay, so we have 1 plus x here. So again, if we zoom out, it will only captures one value, this one here. So let's try another. When n is equal to 2, we have 1 plus x plus 1 half x. Okay, 1 half x squared. Okay, so that one. So remember, now let's zoom out. Let's try to zoom out. Okay, I think I don't know if the intersection between e to the x and this function here, the purple one, will cover some more points in the exponential function. But again, let's try another. When n is equal to this one, 3. Let's copy this one, and let's copy, then add more. Let's say we can add 1 over 6 times x cubed. Okay, so as you can see, more and more points are approximated by the function, this function, the black one. Okay, so meaning to say, if we increase the value of n, okay, if we increase the value of n, n is equal to 4, we have 1 plus x plus 1 half x squared plus x cubed plus, this is 4 factorial is 1 over, I guess this is times 4 is 24 x to the 4. Okay, and so on and so forth. Okay, So let's try to copy this one and add more. Let's say if we can approximate more points, plus 1 over 24 times x to the 4. Okay, so can I pick another color here? Maybe let's try orange, this one. Okay, done. So as you can see, look at the, let's try to zoom out. Let's just look at this one, this red, the original function, which is approximated by this yellow. No, not yellow, not, oh, this is orange. Okay, I think more and more points are being taken by the function, this function, the orange one here. Okay, so as the title suggests, as you can see here, graphical interpretation of representing the functions by a power series. If you look at the graph, okay, let's look at the graph. As n approaches to infinity, so this function here covers more points in the original function into the x. Okay, so that's one of the purpose of the what they call this one, the power series. Okay, so I guess maybe try some other functions like the cosine, and then get the power series, and then play when n is equal to 0, get the value. When n is equal to 1, get the value, and then graph. And then finally you will realize, if you try to add more polynomials here, you can get the what they call the error will be less if you extend the value of n to a bigger number. Okay, so let's have an assignment. Okay, so when you come back again, you will see our assignment for this topic. Okay, number 1. Okay, this is your assignment. We have 4 assignments. And this one, number 1, number 2. Can pause the video to copy the assignment. This is number 2, number 3, and finally this is number 4. Okay, so if you are done with copying the assignments, don't forget to subscribe by clicking that red button, subscribe button, and bell button in the description below. Okay, thanks so much for watching. God bless everyone.
You decide if you ever